aimed at molding the understanding and passion for mathematics among young learners. This is the Equationators, your equation fanatical educators. Greetings, students! Congratulations on successfully completing Quarter 1 of Mathematics. With the conclusion of the first quarter, we now set sail into the commencement of the second quarter, where our attention will be directed towards the realms of polynomials and geometry. This video will focus on Grade 10, Alternative Delivery Mode Mathematics, Quarter 2, Module 1, Graphs of Polynomial Functions, First Edition 2020. With Equationator CAF, you will be guided to making sense of the world that is made up of numbers, lines, and variables. Prior to delving into the substance of our discussion, allow me to say the objectives set for today's lesson. After going through this video, you are expected to describe and interpret the graphs of polynomial functions and graph the polynomial functions. Always remember to take down notes as I discuss. Without further ado, matuto na! Examine these options carefully. As mentioned previously, our attention in this quarter will pivot towards the study of polynomials and geometry. Can you recall the definition of a polynomial? How can one determine if a function qualifies as a polynomial? It is important to bear in mind the three criteria essential for identifying a polynomial function. If each exponent is a whole number, no variable is under the radicand sign, and denominators contain no variable in x, then that function is polynomial. Given these three criteria, can you identify which function is polynomial on the given choices? Pause this video if you need to. Let's go through them one at a time. Option A has a negative exponent, and according to criteria number 1, each exponent must be a whole number. It must not be in fraction form or bear any negative integer. Therefore, option A is not a polynomial. Option B is a function that has a denominator containing the variable x under the numerator 3. Therefore, option B is not a polynomial. Option C contains no radicand sign, but since only the whole number 2 is under the said sign, it does not fall contrary to the criteria that says no variable should be under the radicand sign. The variable x is only beside the whole number 2. Therefore, option C is a polynomial. Finally, option D contains a fraction exponent, contradicting criteria number 1. Therefore, option D is not a polynomial. Great! Did you guess right? After recalling polynomial functions, you will now see polynomial functions and its corresponding graphs. Examine the graphs and corresponding polynomial functions depicted in each figure. Have you ever pondered the origins of these rising and falling patterns exhibited by the graphs? Today, we will explore the leading coefficient test to gain insights into the factors influencing the behavior of polynomial functions. The leading coefficient test is a criterion used to determine the end behavior of a polynomial function. It focuses on the leading term of a polynomial, which is the term with the highest degree. The test helps to predict the behavior of the function as x approaches positive and negative infinity. To better understand what I meant, let's talk about the 4 cases of the leading coefficient test. The table that you see shows the behavior of the graph of polynomial function in standard form. Case 1 showed that if the degree of the polynomial is odd and the leading coefficient is negative, then the graph rises to the left and falls to the right. Case 2 showed that if the degree of the polynomial is odd and the leading coefficient is positive, then the graph falls to the left and rises to the right. Case 3 showed that if the degree of the polynomial is even and the leading coefficient is positive, then the graph rises to the right and also rises to the left. Case 4 showed that if the degree of the polynomial is even and the leading coefficient is negative, then the graph falls to the left and also falls to the right. With that being said, let's put our knowledge to test. What do you think are the end behaviors of p of x equals x cubed minus 12x squared plus 44x minus 48? That's right! The graph falls on the left and rises on the right. Because the degree of the polynomial, which is 3, is odd, and the leading coefficient, which is the imaginary number 1 beside the variable x, is positive. However, before we can accurately depict the graphs, it is essential to determine the x and y intercepts. Without this information, our ability to illustrate the graphs is limited, and we can only rely solely on our understanding of the end behaviors. Using the same polynomial function, let us discuss the steps involved in graphing polynomial functions. To determine the x-intercept, we set y equal to 0 and solve for x. Take note that in this case, f of x, p of x, and y are synonymous with each other. That is, we need to set f of x equal to 0 and then find the values of x that make the equation true. In other words, we are looking for the roots or zeros of the function. The rational root theorem can help us identify potential rational roots. According to the theorem, any rational root of the polynomial must be a factor of the constant term 48 divided by a factor of the leading coefficient, which in this case is 1. So, the possible rational roots denoted as p over q are the divisors of 48, which are positive negative 1, positive negative 2, positive negative 3, 4, 6, 8, 12, 16, 24, and 48. Now, we can test these values using synthetic division or polynomial long division to find which, if any, are actual roots of the polynomial. I personally believe that using synthetic division is more convenient. That is why, using synthetic division, let us extract the rational roots of the polynomial function. Let us start with x equals 1. Since the remainder is not 0, 1 is not a rational root. Now let's try 2. Since x equals 2 is a root, that means that x minus 2 is a factor of the polynomial. The result is a quotient of x squared minus 10x plus 24. Now we can set this quadratic factor equal to 0 and solve for x to find the remaining roots. The next method involves expressing the middle term, negative 10, as the sum of two terms whose coefficients multiply to the product of the leading coefficient and the constant term. Given the quadratic equation, we need to find two numbers whose sum is negative 10. The numbers that satisfy these conditions are negative 6 and negative 4 because negative 6 times negative 4 equals 24 and negative 6 plus negative 4 equals 10. Therefore, the roots of the quadratic equation x squared minus 10x plus 24 are x equals 4 and x equals 6. Combining this with the previously found root x equals 2 from the linear factor, we have the three roots of the cubic equation, 2, 4, and 6. Oh, but our journey doesn't conclude just yet. The y-intercept is just about to be unveiled, and you're in for a treat because finding it is delightfully straightforward. To uncover the y-intercept of the function f of x equals x cubed minus 12x squared plus 44x minus 48, all you need to do is to get the constant term negative 48. Let me simplify the process for you. Substitute x with 0, like so. Negative 0 equals 0 cubed minus 12 0 squared plus 44 times 0 minus 48. You'll get the answer, negative 48. There you have it. Remember that no matter what numbers are in a polynomial, its y-intercept is always the constant term. With your knowledge on graphing polynomial functions, can you now identify the end behaviors of the graph? That's right! As mentioned earlier, the graph falls on the left and rises on the right because the degree of the polynomial, which is 3, is odd, and the leading coefficient, which is the imaginary number 1 beside the variable x, is positive. And that wraps up today's lesson of graphing polynomial functions. This has been your Equationator Cat, saying that you should love math. This is your equations enthusiastic educator, aspiring to inspire love for numbers and problem solving in the hearts of the next generation. Bye-bye!